introduce the idea of angular momentum. This is 11.6 to 11.8. And so we're thinking about vectors. The whole idea about vectors, dot product, cross product are all very important here. And so recall the cross product was AB cosine theta, right? And we had the other way, method 2 of finding the cross product. Well, same thing for the vector product, or sorry, two ways of finding dot product. Now we have two ways of finding cross product, okay? One was AB sine theta, right, like FR sine theta. And then we would find the direction using the right-hand rule, okay? And so that's the first couple. And so then, we know that if two vectors are parallel or anti-parallel, that their cross product comes out to be 0, because sine of 0 or 180 is just 0. And then if two vectors are perpendicular to each other, then it's just a times b, right? Because sine of 90 is 1. And so it's just the magnitude a times b. And then we have these other rules for cross products as well. There's the product rule, distribution, multiplying by a scalar, that kind of thing. Don't forget that order counts. Order counts for the cross product, so this is important. Okay, what if you don't know the angle between two vectors? What if you only have and what if you have them in the unit vector notation, right? IJK kind of thing. You've learned a way, I think in pre-calculus, of how to do this, but I'm going to teach you another way. You can choose either way to do the cross product. Okay, and so A cross B, we're going to set up a matrix, and it'll look like this. I, J, K. So here we're going to have AX, AY, AZ. These are the components of A at each of these dimensions. And then same thing for B. BX, BY, BZ. I put the first one on the top, second one on the bottom. And the way that I do this is I extend this matrix this way. Okay, so I actually make a copy of this over here. I, J. So here's AX, AY, BX, and BY. And to find I, what I do is I go down this way and create this type of thing. Okay. And so the new vector is going to be this. So AY, BZ, I, it's the product of these things, minus, and then I go up through I. So I go down through I, and then I go up through I this way. Minus BY AZ times I. And that looks a lot like what you've learned before, right? You ignore this and this, and you take this times this, or this minus this. So it works the same way. Plus, and now for J, I do the same thing. I go down this way, and then I subtract with minus that thing. So J is AZ BX J minus, and then here BZ minus AX, or times AX J. And that's the opposite of what you learned before, because here we're going this way, like this times this, is that. Before you would learn this minus that, but now we're taking this one first. So you'd have like plus minus plus, but since we're going in a different order, the signs all work out. And then for K, again, same kind of thing. We go down this way, and then up this way. So this is plus AX BY K minus, I go this way, BX X AY K. And then when I put these together, I get my new vector, and it's going to look kind of like this. AYBZ minus BYAZ I plus, and this is not a new matrix, by the way, I ran out of space. So this is, and then AZ BX minus BZ AX J plus AX, oops, that's not an X, AX BY minus BX AY times K. And this now is how you can find the cross product if you don't know the angle and you have everything in terms of unit vector notation. So torque as a vector cross product. Now if we have torque, then it was RF sine theta. Now it's still R cross F, and we can calculate it using this if we have R and F in unit vector notation. And just as a reminder, we have this where if this is R and this is F, then the torque ends up coming out of the board. Or if we have this, again, same thing, R cross F, the torque comes out of the board. And if I have R and then F going into the board, then the torque is going that way to the left. And so this is the right-hand rule for a screw. If you're trying to screw, righty-tighty, lefty-loosey, if you look at the screw itself, the lever arm, right, is out this way, and then F is out of the page, so the torque is down. So that's pushing the screw in. And for the second one, you're going the other way. Here's R, F is coming out of the page, and that's up. That's going to pull the screw out. And so here's an example. You have a force. Okay. So now these are the vectors relative to the origin. And we want to know what is the torque. Well, tau is R cross F. So I'm going to set up my matrix. So I, J, K. This is going to be R, this one first, right? R cross F. So 4, negative 2, 0. And then I have 2, 3, 0. I'm going to repeat over here. We're going to have I, J, 4, 2, negative 2, and 3. Okay, so now I, right, when we're finding I, I'm going to go this way. Well, that's easy. That's 0. So 0 minus, and I go up this way. Again, I get 0. Plus, for J, I go down this way. 0 times 2, that's 0. Minus, and then the other J, again, 0. And then, so now I'm going for K. So I go down this way. So this is 4 times 3. So that's 12 minus, and then I go up this way. 2 times negative 2 is negative 4. So I simplify this whole thing, and I get 16 Newton meters in the K direction. Whoops, let's do that whole thing wrong. I think I'm just about up there, Chris. So tau equals RF. Remember, order counts. And so I set up my matrix. I've got I, J, K. R is 4J minus 2K. So this is 0, 4J minus 2K. And this is 2, 3, 0. And then I repeat over here, I, J, and I just repeat this, those two columns. Okay, so for the I part of it, I get 0 minus, and then this one, this turns out to be negative 6. I plus, for J, I get negative 4 minus, and then the other J is just 0. This is J. Plus, and then for K, I get 0 minus 8. Simplify the whole thing, and I get 6I minus 4J minus 8K. Okay, and now that we're thinking about vectors, we're going to think about angular momentum as a vector and as a cross product. The first definition of angular momentum is L. L naught, that's L is angular momentum around the axis O, or the origin. And L is the letter that we use to abbreviate angular momentum. And we write it as R naught cross P, where P is simply the linear momentum. So R cross P, that's the first way that we can calculate angular momentum. And so this is R mv sine of theta. That's one way of looking at it. Another way, this is R naught cross V times M. And so M can come out front. This can be M R naught cross V. These are all ways of thinking about angular momentum and the way it relates to linear velocity and linear momentum. As you can see, the units here for this are kilograms meters squared per second. Because in momentum, you've got kilograms meters per second. We're multiplying that by meters there. And then another way of looking at this is R mv sine theta. The V is R omega, right? So R m R omega. And let's say if it's at 90 degrees, then sine of theta is 1. So this is actually then mr squared omega. Mr squared is the moment of inertia. So this is I omega, right? Around, so L is also I omega, the moment of inertia times the angular velocity. This now is the angular rotational equivalent of P equals mv. Right? So now we have momentum, angular momentum, mass equivalent, right? The angular equivalent, which is moment of inertia. Instead of v, now we have angular velocity. And we get the direction of this, because it's a cross product, we can get the direction through use of the right-hand rule. So here's an example. We have a 0.2 kilogram particle. So for this example too, we have a 0.2 kilogram object going around counterclockwise, circle of radius 0.1. And so here's the particle, here's the path as it goes around. Now let's just find the magnitude and direction of the particle's angular momentum relative to the origin. So L equals I naught omega, right? O for O, the origin. That's not a perfect circle, as you can see, but let's imagine that it is. So I need to know what omega is, but I don't have omega in radians per second. Instead, I have revolutions per minute. So I need to convert this. So 15 over pi revolutions per minute. When you convert that, I believe you get half of a revolution per second. Actually, one revolution is 2 pi radians, and then 1 minute has 60 seconds. So here the pi's cancel out. 15. So this is 30 over 60. So this is half a radian per second. So omega is half a radian per second. And what's I? Well, it's a point particle, so it's just mr squared. So mr squared omega. M is 0.2. R is 0.1. And omega is 1/2. I'm left with 1 times 10 to the negative third kilogram meters squared per second. And the direction is in the positive, so I can put positive here, or I could say counterclockwise, or you could again do that, indicating the direction of the angular momentum is pointing out of. Now, strangely enough, we can talk about the angular momentum of a particle that's moving in a straight line. For example, this one going this way. Right? How would this have angular momentum around this? Well, the way we calculate it, L is, remember, mv or rmv sine of theta. If r is here, then this distance, the distance from the origin, that gives us, r sine theta gives us this distance. And so it's kind of like torque. It's like I'm looking for the perpendicular component, or the component of the radius that's perpendicular to the line of action, the velocity of the point particle. And so here, this ends up just being dmv as the angular momentum. And so we see this in example 3. Let's take a look at that now. And so here's example 3. We've got a few ways really to solve this. First, let's look at this as just a cross product using the unit vector notation and what we need to set up the matrix. So L equals R cross B, which is going to be M R cross V. So I'm going to take the mass, put it out here, and then I'm going to multiply that by R, so it's negative 4. Here's I, K. So negative 4, this is 3, this is 10, 0, 0, 0, all this stuff. So then I, K, negative 4, 3, 10, 0. And so when I do this, I notice that that's 0, that's 0, that is 0, that is 0. So the only thing I'm left with here is 0, it's negative 30, it's supposed to be K, negative 30K, and the mass is 1 kilogram, and so 1 times this will just be negative 30. Negative 30K kilogram meters squared per second. So there we have the angular momentum found using this. Another way to do this would be to take this distance, right? If this is the velocity, this is the perpendicular distance. That's 3 3 meters. And so I would take R times V times M, right? R, M, V, which would be 3 times 10 times 1, that gives me 30. 30 kilograms meters squared per second, and in what direction? So we've got to do R cross V, and I get this going into the board. Into the board then is this, or we could say that it's clockwise, or it's in the negative K direction like here, right? What's negative K? It's into the board, which we find that same thing using the right-hand rule. The other thing to do is to use R cross P, right? So what's the momentum? 1 times 10, so it's 10 kilogram meters per second. And then if you want to take, this would be 5 meters, but 5 sine of theta, if you want to do R and V sine theta. Remember this theta here, this is a 3, 4, 5 right triangle. So sine of theta is just 3, so you end up doing the same thing as here. So that's example 3, and you can see a bunch of ways to look at it. Okay, here's example 4. We have a 1 kilogram particle moving 5 meters per second to the right. Below here, half a meter. So we want to know what is the moment, or the angular momentum relative to the origin of this particle. So this is the origin. L is going to be, again, R, mv sine of theta, but again, this is 90 degrees here. Right? This distance will always, this 0.5 meter distance will always be the sine of theta, whatever angle this is, right, as it continues to move along. So we just have to do R mv. So this is 5 times 1 times 5, so we get 2.5 kilograms meters squared per second. And what is the direction? Well, here's R, here's V, so it's coming out of the board. So we could write K like that, it's positive, indicate that way, or again, this is counterclockwise, or the positive direction, or coming out of the board. Okay. And then in linear mechanics, F, right, the momentary force, was the time derivative of momentum. Okay, and that's true here also. The net torque is the time derivative of the angular momentum. It's R cross F. It is UL. And now for example 5, we have this penguin that's falling. There's a distance here, so from this origin, how is he falling? First we want to know the angular momentum as a function of time. This is interesting. Well, we know that angular momentum, this is the origin, angular momentum is R mv sine of theta. Well, R sine of theta, if this is R, theta, theta is this angle here, right, making between the velocity and R. The sine of that is just going to give me D. So R sine of theta is equal to D in this point. That's the distance to this line of action. So this is just going to be dmv, but at the same time, v is equal to gt. Right? The velocity is however long it's been falling multiplied by g, and so this is dmgt. That's the function for the angular momentum of the penguin as it falls about this axis. Now we want to know the torque on the penguin about O due to the gravitational force. Well, torque, oh yeah, and this, by the way, R cross V, this would be into the board. So this could be, let's say that it's clockwise. torque is R cross F. Well, R, again, we're looking for the component of the radius that's perpendicular to the force. The force is down this way. R, this is the perpendicular component, again, D. So this is going to be dmg. Clockwise. And that's it for our lesson on angular momentum.